video is show you how to do Lewis dot structures with the concept of resonance. Resonance is when there's more than one valid Lewis dot structure for a molecule. So what that means is when you're done drawing the Lewis dot structure, there'll be more than one correct answer that you may have to record both answers, or if there's even 3 answers. So again, if you want to pause the video to record the dot structures rules, I did a video on just Lewis dot structures, so you could watch that video in addition to this one. So we're going to get started with an example. The example that we're going to do is sulfur dioxide. The first step is counting up the number of valence. The group number 1A, 2A, 3, 4, 5, 6, 7, and 8A, called the main group, have the same number as the valence electrons. So in this whole family, this family where oxygen and sulfur reside, they all have 6 valence electrons due to their electron configuration. So there's 6 for sulfur and 6 for oxygen. So I already totaled them over here. So I'm going to have 9 pairs of electrons to place, or 18 total electrons. I also already kind of counted the electrons out right here. I have 6 for the sulfur. I'll let those be those orange ones. And then I have 6 for each of the oxygens. And then my next step is to decide which element goes in the center. Well, it's usually the one written first, or it's the one that has the lowest electronegativity. The next step in the dot structure is to place a pair of electrons between the atoms to make them bond. So I'm going to place those. So that means the oxygen is bonded to the sulfur, bonded to the oxygen in this dot structure model. The next thing is kind of good to know that oxygen will typically have 2 lone pairs. So you may want to just place 2 lone pairs around the oxygen. The next step is that the sulfur only has 4 electrons, so I'm going to place these 2 there. That allows currently each atom to have 6 electrons around it in its dot structure. But the rule is called the octet rule. So again, we're still going to have to obey the octet rule right now. And that means that every atom wants to have 8 electrons around its dot structure. So what I'm going to do is place these next electrons on the outside of this oxygen, and what that does is it allows this oxygen to have 8. And if you felt like maybe you want to do the same thing for this oxygen, it will be wrong, because now that one has 8. The problem with this dot structure is that the sulfur only has 6. So you can't place both pairs on the outside of the oxygens. One of these pairs will have to go into the middle and be shared to make what's called a double bond. But with resonance, this oxygen here could have just as likely donated that pair. So if these were here, then this oxygen would have to donate its outer electron pair called a lone pair. And that is the definition of resonance. It's where this would be a correct answer, or with this sulfur bonding to that oxygen with a double bond instead of bonding this way with a double bond. So I'm going to show you how to write that without the little kit. So what it would look like again is you have your atom in the middle, which is sulfur, and then I have my outer atoms and their oxygens. And then I had the electrons were placed a pair between them. And then the next thing I did was I placed a pair on each oxygen, 2 pairs actually. And then my following step after that was I gave sulfur 2 electrons so that each atom had 6. But I had 2 pairs left, so I placed a pair here. And then I can't keep that pair there, otherwise the sulfur won't have 8. And again, what happens here is that makes a double bond. So if you wanted to, you could just connect these and show that that's a double bond, and that's a single bond. But that isn't the only right answer. If this molecule has something called resonance, you draw a kind of like a double-headed arrow, and a lot of chemists will put these in brackets. And then the other answer was, again, still sulfur in the middle and oxygen left and right. And then you're still going to have a bond here and a bond here bonding them, and then the 2 lone pairs on the oxygens to start, and then that one on the sulfur. But instead of having the electrons there, this oxygen could have a lone pair, and then this sulfur here would have a double bond there to this oxygen, and then that one would be a single bond on that side. Now, there is another option. There's another way to show this. There is a way to show both of these structures at the same time. And so what that looks like is it looks like this. You have a sulfur and then an oxygen, and then an oxygen. And you have the lone pairs shown the way they were before. But what's different is they'll show a single bond on this side and this side like that. And then to show that that double bond can be located either here or there, they will draw a dashed line like this. And the reason why this is a valid Lewis dot structure, it's showing that both are still possible kind of half the time. And so what happens here is that this is still another way to show it, and it's still 9 pairs. 1, 2, 3, 4, 5, 6, 7, 8, 9. It's just you're showing a half dash line saying it could be in either position. The other thing that's nice about this is double bonds are sometimes given the bond order of 2. And then a single bond would be given what's called a bond order of 1. And then what happens is if this resonates or moves between these, what really happens is that really these bonds are really like a 1.5 bond order, because they really could be in either position. So you can show it, the resonance this way, or you could show it with one step by drawing that with dashed lines instead. The next molecule we're going to do is sulfur trioxide. So it's called sulfur, it's a covalent name. Tri meaning 3 oxygens. You don't have to worry about electrons being gained or lost. These atoms are sharing electrons. So again with this one, you'll have a sulfur in the middle, and then oxygen on either side, and then you can place this top or bottom. I'm just going to place it on the bottom. You still have to count the number of valence, so it's still 6 electrons and 6 electrons times 3. So now we have a total of 24 electrons to place, or it'll be 12 pairs of electrons. So I'm just going to again bond these atoms, 1, 2, 3, 4, 5, 6, or 3 pairs. I'm going to give the oxygens their 2 sets of lone pairs. So I'm going to stop and kind of total up what I have right now. 1, 2, 3, 4, 5, 6, 7, 8, 9 pairs. I only have 3 pairs left. So if I start by placing the electrons on these outer oxygens as lone pairs, that was my 10th and my 11th pair. So I only have 1 pair left. And if I place it here, this sulfur is only going to have 6 electrons around it. So this last pair also has to be placed in what's called a double bond. Now, that oxygen currently has the double bond, but this molecule has 2 other answers. And I'll show you why. So this one would have 3 valid Lewis dot structures, or would have 3 resonance structures that are all valid. And what they would be again, you'd still have them all connected like this with a single bond. You'd still have your oxygens with your lone pair. The difference is this double bond is going to be somewhere else in the molecule. So this oxygen can have a lone pair, but maybe this one has to double bond, and then the last pair goes there. Let me just check that I have, again, 12 pairs. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then, kind of as maybe you predicted, the last double bond would resonate or rotate or move through the structure and would be over here. And then this would go back to being a single bond with 3 lone pairs. And this would be a single bond with 3 lone pairs. So these would be the 3 valid Lewis structures for sulfur trioxide. And again, we're representing a concept called resonance. And if you say, hey, is there one way to show all of these at once? And there is. So what you'll do again is put your sulfur in the middle and oxygen on each side, and then down. And so you have, again, 2 lone pairs on each of the oxygens. And of course, they're going to be bonded at least once to make that single bond every time. But then what happens is that that double bond could be in any of these positions. So what will be shown is just these dashed lines. So these are dots. These are kind of a dashed line. That's showing that that double bond could be located in any of those 3 positions. If you want to check again to see if it's 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So these dashed lines kind of count as a pair. They're just not a permanent pair. If you did something called bond order with this one, again, these would be double bonds and single bonds. What's going to happen is that really with sulfur, there are 3 of these kind of a bond that's a single and then not quite a double because it rotates 3 times. So it'll have what's called a bond order of 1 and a third. Or you can say 1.33 repeating, but the bond order is, it's not a single and it's not a double. These are all equal in length too, so that's also important that all 3 of these bonds are what are called equal in length. So I hope these 2 examples of resonance helped you. Again, remember that I did still follow the dot structure rules. And I did have to reference the periodic table to look up the valence electrons using those group numbers as kind of a shortcut. And I hope it helped.